Pressure, volume, and temperature relationships are interesting. Let's try this problem. Calculate the pressure in kilopascals. That's a pressure unit. That is the SI system. 1,000 times a pascal is a kilopascal. Exerted by this mass, 1 gram of carbon dioxide, which is a gas, in a flask of volume 1 liter at 300 degrees Celsius. Okay, so in this problem they want us to calculate the pressure in units of kilopascals. So let's see what we have here. Is this a two-state problem or a one-state problem? Well, looks like it's just a one-state problem. We need to calculate the pressure in a particular amount at a particular temperature and a particular volume of this given gas. Okay, so let's just write down what's given here then. We have let's see, the volume is equal to 1 liter. The temperature is equal to 300 degrees Celsius, but of course that always needs to be expressed in Kelvin. So that's really 573 Kelvin. The let's see, the pressure is what we're looking for. In particular, we want it in units of kilopascals. And the number of moles, normally when we are working with the gases and we have several conditions, we can calculate the other condition based on the ideal gas law. But to do that, the quantity needs to be expressed in units of moles. Okay, we don't have that. What we have instead is 1 gram of carbon dioxide. All right, so if I had the moles, I could find the pressure using the ideal gas law, PV equals nRT, and rearranging and solving for pressure, nRT divided by V. Okay, so the problem is I need to figure out the number of moles first. I have the volume, which I can plug in right here. I have the temperature, which I can plug in right here. The R, now the R, I have in a table. In particular, R is calculated in different pressure units, and there is an R readily available from a table already calculated using instead of liters atmospheres mole Kelvin, it's liters kilopascals mole Kelvin. And if I look that up in a table, that particular R is equal to 8.31447 liters kilopascals per mole Kelvin. So I have that available to me. The thing I don't have is the moles. I'm just going to have to work it out. Okay, so I'm looking for the number of moles of carbon dioxide in, how much do I have here? 1 gram of carbon dioxide, 1.0 grams of carbon dioxide. Okay, how am I going to figure that out? Well, I can look to the periodic table, and I can calculate from the periodic table the molar mass of carbon dioxide. The molar mass of carbon dioxide is the sum of the molar masses of all of the components in carbon dioxide. So carbon from the periodic table is 12 grams per mole. Oxygen from the periodic table is 16 grams per mole. But in this case, I have 1 carbon and I have 2 oxygens. So if I add all of that up, the molar mass of carbon dioxide comes out to be 44 grams per mole. All right, so if I know I have 1 gram of it, I can determine how many moles I have by converting from grams to moles. 1 gram of carbon dioxide, for every 1 mole of carbon dioxide, it weighs 44 grams, according to the molar mass. The gram unit cancels, and when I do the math, I end up with 0.0227 moles of carbon dioxide. So that's my N. That's how much moles of carbon dioxide I have in this particular flask. So I can put that back up. All right, so N is 0.0227 moles. So I can plug that in for the N. Now I have everything, and I can calculate the pressure. the pressure in kilopascals exerted by 1 gram of carbon dioxide is going to be equal to, when you plug it all in, 110 kilopascals. All right. So using the ideal gas law, recognizing that this is a one-state problem, I can solve for P using the R with the kilopascal unit, calculating for N simply by looking up the molar mass of carbon dioxide and converting to moles of carbon dioxide here. I can calculate that the pressure is 110 kilopascals.